Hi everyone. So what we're going to do is discuss this paper, and the paper is about a model named Tacotron2, as you can see, and the paper is built on a previous paper named Tacotron1. Yep. So what this paper actually does is, let's just read and then we will know. So it proposes a neural network to synthesize speech directly from text, and that is the goal here, and the goal was same for Tacotron1 also, but in this Tacotron2 they make the simple system compared to Tacotron1, and the system of Tacotron2 has a RNN that maps the character embeddings to MEL scale spectrograms. So you should know this thing. So what they have is, let's say, an input is the characters. What they do is they learn, pass it through some function, and they get embeddings for all of them. Once they have the embeddings, what they do is they pass this to a system called RNN, and the output of RNN is a spectrogram. So this is how they do it. Pretty simple system, and then they calculate the loss over this. Pretty simple function. Okay. And after you have this thing called spectrogram, and to be precise, it is MEL scale spectrogram. What we do is we pass it through a vocoder. In this paper they used wavenet decoder that converts this spectrogram to the real audio that we could hear and process as humans. Okay, and these are like two different steps. So in the paper they just proposed this thing. That's it, they proposed this. This is trained separately on these predictions. And what they show is that their paper achieves MOS of 4.3, which is good. And compared to real audios, they are very close to them. They also present some ablation studies of key components, and yeah, that's it. And they, as they said, they only use MEL spectrum as input to the vocoder wavenet, and they don't use any linguistic or duration or extra features, just simple old ways. We further show that using this compact acoustic intermediate representation allows for a significant reduction in the size of wavenet architecture. Nice. This is very important. Okay, so as the Tacotron is a sequence-to-sequence architecture because of the RNN, and it produced magnitude of spectrograms from sequence of characters, as I showed you. So you have some characters, and then you produce the spectrogram using RNN. And then what you have is a vocoder which converts these spectrograms Okay, so now they're talking about Tacotron1, not Tacotron2. And previously also they were talking about Tacotron1. And in the second one they use Griffin-Lim algorithm to convert them to inverse Fourier transform and then to the audio. In this paper they follow, as they say, similar to Tacotron1. They do the text to spectrogram followed by a modified wavenet vocoder, as you can see, which is trained directly on normalized character sequences and corresponding speech waveforms, and the output is very good. So Deep Voice 3 is a very similar approach, but the Tacotron2 evaluation shows that it rivals of human speech. Then there's another thing called character to wake, using a neural vocoder. So they have a neural vocoder, and it's a completely end-to-end, and it's a little bit different. Yeah, you have to read this paper if you want to know about more. So what do they have? Okay, before this, let me start here. What they have is, so given input text, you get some embeddings, pass it through convolution layers, and then LSTMs. So this output representation that you get after the encoding is like contextual embeddings of the input text. That's it. Nothing more, nothing less. So this is, you could think of a simple language modeling, but how it is learned is from this gradient, not from some language modeling loss. That's the only difference. So this is just like some contextual embeddings of the input text that are suitable to produce this null spectrogram. Okay, and once you have these embeddings, what you do is you have a decoder with two LSTM layers. So for each of the inputs, you apply two linear projections. Please keep in mind linear projections. And if the output of the second one is stop token, that is, the probability says that yeah, you should stop, then you just stop. But if it is not this, that is, the path goes like this, then what you do is whatever the output you get from this LSTM, you pass it through 5 convolution layers, which they call postnet, and you use this as a residual connection. By residual connection, I mean the residuals from the, so let's say you have this input. Now instead of just using this input, you do some things and add it to it. So now it would be something like previous plus. So what to add to this thing to get this output? Yep. Okay. So once you have this, instead of feeding the projection output of this LSTM, what they do is they take the previous one, pass it through a 2-layer prenet, and then they feed it back to it. Okay, so I think we can spend some time on it. Let me add maybe a page. Yep, I will do that. Okay, so what you have is this. So you have some encoder, text, you get some embeddings. So this encoder is until the LSTM, and then what you have is a decoder. This is like RNN, and then what you do is for some input, let's say you start off the sentence. Okay, you have this embedding with you, and then how does it come? So you have this okay, so this is the attention thing, like the weights that you get for the input. You get some output, you pass it through 5-layer system to get the output, and then what you have is this input. This input, what you do is before feeding it to the next one, what you do is 2-layer prenet, and then it's like step 2. You have and this is what you have. Of course, again, the attention goes to the next step also. and you just repeat this process again and again and again. So that's how things are working. And yep, simple architecture, very simple, but the attention that they use is location sensitive. We should know about this. And yeah, apart from this, everything else is just like the architecture. So as you can see, this is the character embedding, simply 512 dimension, one layer. Then they have 3 conv layers. The 3 conv layers is just each containing this many filters with shape 5,1. So it can look at 5. This is just the kernel size. And then the bash norm and real actuation to make it non-linear. Then they have LSTM, the output of final. So this is single one LSTM to have more context. That's it. You could add more conv layers to have more bigger context, but they use LSTM. Oops. Okay. After this, what do we have? We have this attention. And also the prediction from the previous timing step is first passed through a small tree-net containing 2 fully connected layers. Yeah, as you can see, simple 2 fully connected layers of 256 hidden value units. That's a 2-layer MLP. So I could say MLP 2 layers. And then what you have is, as I said before, the processed input from the previous step and the attention context vector. So you concatenate them and pass through a 2 stack of unidirectional LSTM layers. Okay, this is new. So they are just like simply concatenating these things. Okay. So yeah, this is the linear layer to predict spectrogram. This one. The is passed through a 5-layer post residual to add, as I said, simple number. Each post layer is comprised of same number of filters, 512, with a shape of 5,1. Yeah, this is very similar to this conv layers. So this is simply do the MSC loss and after the post network convergence. This just loss. This I don't know why would they write that. They also applied a log likelihood loss, and it didn't give them anything to be happy for. So they just like use a simple MSC. And lastly, in parallel to spectrogram frame prediction, the concatenation of decoder LSTM output and the attention is projected down to a scalar and passed through a sigmoid actuation to predict the probability that the output sequence has completed. Okay, so to predict this thing, what they do is the concatenation of decoder LSTM output and the attention context is projected down to a scalar. Yeah, so this is new. So they take the context vector, I think, from here, concatenate the output projection, and then they do it to get the stop open probability. This is just to say, okay, I want to end right now. Yeah, and then you have this probability 0.5. If it's more than that, then you stop. If less, then you continue. So the convolution layers in the network are regularized using dropout. So in CNN they have a 0.5. So probability in the first time report with probability layers in the pre-net of photographic decoder. So what they do is they also apply a dropout in the input. But for the pre-net, that's it. And this is different from original Tacotron because it's very simple. They don't use any CBGs, all those things that they used before. And this is vocoder. I wouldn't go much into this. I just expect this WaveNet. That's how they do it. If you read it, it's easy. Okay, so how do they do it? How do they train it? I think they use TJ forcing, so like do not use the predictions but use the real spectrogram output from the previous step. This is for the atom, that's it. And so there it is. Yeah, this is L2 weight decay. So what they do is after this, train the WaveNet, but on the ground truth aligned predictions of the future prediction network. So they use this whatever the output you get from this thing to train this. Just to do what? So this ensures that it aligns with the target waveform samples. Yeah, nothing more. Yeah, this is important. 32 GPUs, very big batch size. So if I have to do, this would be 32 times 128. Let me just use my calculator to quickly do that. 4096. This is 4096, guys. That's the batch size they have. And after that, what they have is nothing of interest, and that is it. Oh yeah, of course they apply a normalization to text. This is more of like how to tokenize the input. Nothing has to do with the Tacotron2 or speech synthesis in general. Okay, so they do some evaluations. None of it is of no use to us. Okay, they compare with baseline, parametric, production, Google. So the system outperforms everything. So parametric is 3.42, Tacotron yes this concatenative. Okay. So okay. It just beats everything. So you have WaveNet, which is conditioned on linguistic features. So and yeah, the Tacotron2 just beats everything out of the water. Okay, so they also do this for each pair of utterances. Writers are asked to give a score ranging from -3 to 3, much worse than the ground truth. The overall mean score comes out to be -0.27, shows that writers have a small but statistically significant preference towards ground truth over algorithm, since it is negative. Little breakdown. The comments from it indicate that occasionally mispronunciation by our system is the primary reason for this preference. This is important. Mispronunciation. And about the same, much better. We ran separate experiment on the custom 1000 sentence test. Okay. 0 sentences contain repeated words, 6 contain mispronunciations, 1 contained skipped words, and 23 were subjectively decided to contain unnatural prosody. Important, like for the improvements to do in future paper. On the wrong syllabus or unnatural pitch. And prediction failed in a single case on the input sentence containing the most characters. The results show that while our system is able to reliably and attend to the entire input, there is still room for improvements in prosody modeling. Important. Again, let me say this. Let me do it like this. Okay. Okay, yeah, this is also important. Out of domain text. On this task, our model receives 4.18. Our side-by-side evaluation comparing output these systems also shows a virtual tie. Our results by examination rater something of no interest to us, except this line. Why we need large datasets. Reason. Okay, let's move forward. While the two components were trained separately, the WaveNet component depends on the predicted features for training. An alternative is to train Waver independently. Yeah, so here they just use the real ones, and what they see is that it's worse. So during training they use predicted, and then they do the prediction synthesis, they do the prediction. Okay. I guess when you have predicted, good. So they were trained using predicted, but synthesized using ground truth. There's a decay. Training was done using ground truth, and synthesis was done with. So predicted gives you 4.5, ground truth gives you 4.5, and the other thing you do is a mismatch. So during training they use ground truth. Prediction is 4.3, very bad. Training on ground truth features and matrices from predicted features is worse than the opposite due to the tendency of the to be over smooth. And this is also then the ground truth. The squared error loss when trained on ground truth function that does not learn to generate high quality speech waveforms over smooth features. Okay. What could we learn from this? So you use predictions and then you generate predictions. Good. But let's say you used predictions for training and then you use ground truth for synthesis. There's a drop, but the drop is very high if you used ground truth and then you try to predict, and they use the prediction. So yep. And students say, yeah, one more thing they do is they don't use the MEL scale, and then what they show is that yeah, you need MEL for a little bit of improvement. And if you use Griffin name, the vocoder is the main thing. Much higher quality, however, there is not much difference between the as such claims to strictly better to less will explore specific audio quality in the future work. Yeah, people could do that. Last thing, what they do is they remove, I think, the post-processing network, and so is it important? So they get 4.4, and yeah, important. Yeah, so they reduce some things and then they say, yeah, still it is better. They reduce the layers, the number of cycles are increased, dilation cycle size reduced from 10 to 6, receptive field is reduced, but still they're able to get very good results. This just means that the spectrogram are generated using the contextual information, and they do retain that information. So that's why you don't need that big of a receptive field anymore. Okay, I think, yeah, this was a good paper. So if I have to put things in perspective, that it is autoregressive, as you have to do step by step here. You can get this from BERT. So yep, that's one thing. This is the location sensitive attention. Yep, this is like a most important part of this paper. Let me just go through it again. Okay, so what is this? This is simply this thing. This extends the additive attention. Additive attention is simply you do average, but now all of the compounds are not equally weighted. When you do average, you weight them. So let's say you have two things, 1 and 1. Now if you take an average, you get what? 1. 1 plus 1 divided by 2. Okay, but now what if I say that the first one is 0.8 and the next one is 0.2? Multiply with each of them, and then what you get is 0.8 plus 0.2. Okay, and then when you take an average, what do you get? 0.5. So now you have scaled these numbers first, and then you took an average. So this is no contribution from the first one. It adds to it something. Attention weights from previous recorded time steps as an additional feature. This encourages the model to move forward consistent with the input. Mitigation potential for errors. Simple, like this just says that this just says this thing. When you are here, you say that this is important. When you are here, you say that this is important. Because if I say my paper is good, and then you generate this spectrogram for this. This good won't be here, we know for sure. You should start from here, and then the next step should not look back. So this should not look back if there is anything. This should only move forward. This is just what it means. And I guess, yeah, that sums up this paper. A very well paper. Shows that simple models could give you the best results.